Is there scientific evidence for God's existence? Both the Old and the New Testaments tell us that God has revealed himself to us through the record of nature. But what does that look like when we study the world around us through science? What kind of evidence constitutes God's handiwork? I'm joined today by Barry Wynn, who is a Christian and a chemical engineer, to help unpack those questions. Barry, thanks again for joining us.
Great to be here.
You know, you are a chemical engineer, but you worked with phosphates and phosphate chemistry. And I think people might be surprised to realize or to learn that even when we look at the phosphate molecule, we see evidence for design, we see evidence for God's handiwork.
Yes.
So first of all, before we unpack that, what are phosphates?
Okay, well, phosphates, that covers a large number of chemicals. You can consider inorganic phosphates and organic phosphates. Phosphates in general are based on the phosphorus and oxygen atoms. One phosphorus, 4 oxygen atoms, making the PO4 ion. And inorganically, we find it in various minerals here on Earth. Fluorapatite, hydroxyapatite are the two main ones. And then we have in our everyday life, we have simple inorganic phosphates in our toothpaste, in our fire extinguishers, in our fertilizers. And in addition to that, we have the organic phosphates, which form very important molecules within living organisms.
Sure.
Which
so phosphates are everywhere around us. It's part of our daily lives.
Yes.
But again, phosphates, as you're alluding to, are part of living systems. And in fact, as a biochemist, I can tell you that they're indispensable for life. In what way are phosphates indispensable for life?
Okay, well, in all living organisms, we have cells. And first of all, there's a membrane around the cell, which is made up of phospholipids. So obviously, phosphorus is present in the cell membrane. Secondly, living organisms have DNA or RNA. And that's necessary in order to preserve information for building the cell and for eventually reproducing. And so phosphate is present in the DNA and RNA of cells. Thirdly, we have energy storage requirements. And the chemical ATP and ADP, adenosine triphosphate, adenosine diphosphate, they work together to store energy and release energy when the cell needs it. Again, a very important phosphate. Finally, vertebrates have calcium phosphate in their bones, their teeth, cartilage, sinews. So phosphate, there are 4 very important requirements for phosphate.
So if it wasn't for phosphates, life wouldn't even exist.
We wouldn't be here, no.
Yeah, and not only that, but we couldn't have complex multicellular organisms like animals.
That's right.
Because of the indispensable role phosphate plays in the skeletons.
That's right.
Okay. Now, how are phosphates ideally suited for life? In what way do we see design when we look at phosphates?
Okay. One feature of phosphates which is important is the fact that they can ionize in the pH range which is consistent with cells. In other words, within the pH range 4 to 10, you can get ionization of the phosphate molecule. And it's really around pH 7 where the H2PO4 ion has its dissociation constant. And important to the performance of these molecules within a living cell is having a charge. For example, in the DNA, the ladder, sides of the ladder are phosphate and ribose molecules, and then of course there's the nucleotides that are the rungs of the ladder. And the phosphate can bind those 2 nucleotides together and still have a charge, and that charge is important for stabilizing the DNA molecule and also making sure it stays within the membrane.
Now, let me just stop you there real quick, because this is a really important point, because phosphate is unique in this capacity, right?
Yeah, that's right.
Because, it's interesting because another molecule that would be an analog to phosphate would be sulfate.
Yes.
And it can form 2 bonds in the same way that phosphates can, but when it does that, it doesn't have a negative charge.
That's right.
So you can never have DNA built from sulfates. It
That's
has
right.
to be phosphates.
That's right. And in fact, if you look at other members of the group, like arsenic, for example, same group as phosphorus, we don't get the necessary ions, if you will, that will ionize and perform what the phosphorus is doing. So it is rather unique in its ability.
And so that uniqueness would reflect design.
Exactly.
Yeah.
That's right.
Okay, so what are some other ways that phosphate is ideally suited for life?
Okay, well, I guess you could say we've talked about the pH range and the charge. The cell has a lot of very complicated chemical reactions going on, and often there needs to be intermediates. Mm-hmm. And the phosphorus intermediate can actually be in the form of even a metaphosphate, which still has a charge, but it can help take one reaction to the next step. So it has a range of possible combinations in the 5-valency that enables chemical cycles to take place.
Yeah, so even when we're looking at molecules like phosphates, which we may not give second thought to,
right.
It's amazing how uniquely structured they are, and if it weren't that way,
yeah.
Life wouldn't be possible.
That's right. And one interesting little side note is when Watson and Crick were trying to unravel the structure of DNA, they were really in a race with the famous chemist Linus Pauling. And Linus Pauling published an article proposing a triple helix. But when Watson and Crick looked at his article, they realized, there's a major blunder, because he did not show that one hydrogen atom that could be released and give a negative charge. And they realized, that's not right. And so just a few months later, they finally came up with their double helix, which of course was the correct structure. But that understanding of the importance of the phosphate and having that extra charge that can be used to stabilize a molecule is key.